So in most cases, you are going to see the applications of the cosine rule, and that is another part that you actually need to understand. We are given these formulas, but we also need to prove these formulas. So as we do understand, the sine rule had a part which it played before, a role that it played, where you are given A and its corresponding side A, and you are given B and its corresponding side B. We can use the sine rule in that case. But we are going to see a condition which is totally different. We have a condition of this nature where you are given a side, another side, and a special angle in between these two sides, which is referred to as the included angle. Then you're asked to calculate the third side. Then you see that no matter the way that you want to use your sine rule, it is limited because it must have an angle and a side corresponding. Then this part must correspond, of which you won't be given this angle. So it means it's impossible. This one you are given, but you are not having this angle, which is also impossible. Meaning to say, in that case, the sine rule is limited. That is where we can think of the operation of the cosine rule, which states that in any triangle ABC that we might be given, A squared is equal to B squared plus C squared minus the product of these two, which is 2BC, the cosine of A, which we are given these formulas. They can also be given in terms of B squared, which is equal to A squared plus C squared minus 2AC, the cosine of angle B. We might be given in terms of C, which is C squared is equal to A squared plus B squared minus 2AB, the cosine of angle C, the angle that you are calculating. These are formulas that we can use in calculation of the sides, where these A, B, C are the sides to be calculated. When it is of the angle that is to be calculated, you are now given the cosine of A is equal to B squared plus C squared minus A squared over 2BC, which we are going to talk about in calculations, actually, when we are using these formulas in calculating the sides and angles. We shall explain much about this. So for now, we need to prove how can we obtain these formulas. All right, just like what we saw in a in the non-right angle triangle, in the proof of a sine rule, you worked with the non-right angle triangle, which is the same part that you're going to do in this case. We are simply working with a non-right angled triangle. That's a non-right angled triangle that you're going to have. And let us consider this being an acute angled triangle, just like what we had before, working with an acute angled triangle. All right. So having an acute angle triangle, it is simply an angle that is less than 90 degrees that you're going to work with. Let us say we've got triangle ABC. Want to see how these formulas are going to be formed. So this is your triangle ABC. In this case, we said if this is angle A, the side opposite is going to be side AB. This will be B, this is C, and this will be C. And we shall just make some constructions from A to the base BC having a perpendicular height H. Perpendicular meaning to say it is at 90 degrees. So these are constructions made that are not part of our diagram. So we're just gonna have this construction to be made. So you're just gonna let AD to be equal to the perpendicular height, which is H, like I mentioned before. This is the perpendicular height, which is simply the height of triangle ABC. So that is the height of triangle ABC with BC as the base. So with BC as the base. So that is with base BC. That is what you can see from this part. All right. We want to see the relationship here that's going to happen. We need something that has to do with a cos. We need something that has to do with a cos. Take note, a cos, something that has to do with a cos. And that is very difficult for us to work with in this case, because we are going to have the cos ratio, but it is not going to give us this particular situation like what we had on a sine. But let's consider to say we take this from D to C, we take this to be X. Okay, let this be equivalent to X, which is the distance from this point to this point, X. Remember, this is A, which is taken from point B to point C. It is A, the distance that we are given from B to C. And X is taken from D to C. What does it mean? It means the remaining part can be calculated as the difference A minus X. So meaning to say the remaining part is A minus X. That is the remaining part from B to D. The remaining part is going to be A minus X. The difference, remember the whole of the line is A and this one is X. So meaning to say as we let AD to be H, we are going to also let this DC to be equal to X. So therefore, that means from B to D, we now have the length given as A minus X from B to D. All right. Consider this triangle, which is the first triangle ABD. That's a right angle triangle. And this is also a right angle triangle. All right. We are going to notice that the Pythagoras theorem can work in evaluation of something here. All right. Let us think of the Pythagoras using the Pythagoras theorem from our Pythagoras theorem. There is a theorem there, Pythagoras theorem. We are going to notice that in this triangle ABD, so you're going to start take that triangle ABD. In triangle ABD, we are going to have, remember, the hypotenuse squared. The hypotenuse squared. If you're given hypotenuse squared is equal to side squared plus side squared, that is hypotenuse squared. So the hypotenuse is C in this case, in triangle ABD. So C squared is equal to the sum of these shorter sides being squared. So that's the A minus X and this H squared. So we've got A minus X in a bracket squared plus H squared. So this is from triangle ABD. Let's see from triangle ADC. All right, from triangle ADC, using the same Pythagoras theorem, we are going to notice that it can work again in triangle ADC. That is in triangle ADC. Using the same concept, we are going to have our Pythagoras being the hypotenuse squared, which is B squared is equal to these shorter sides squared, the sum, which is H squared plus X squared. We have formed something from triangle ADC using the Pythagoras theorem. Okay, now I want us to notice something here because there's something that we can have in common from these two triangles, or from these two that we have formed, from these two formulas of the Pythagoras. We have written this where we've got C, A, X, and H. There we have got B, H, and X. What if we expand this and take something from this formula? Is it going to be B? Is it going to be H? Let's see what we can relate. Remember, this guy is from this one from a grade 9 there when you expanded this bracket of A minus B squared, which is the first squared, minus 2AB plus B squared. Remember how you expand this. So it is the same situation that you're going to have on this A minus X squared. So meaning to say C squared is equal to, let's expand. So that is going to be A squared minus 2 times the first and last, which is AX, plus the last squared, which is X squared, plus H squared. So this is what if this is, guys, we are used to these identities under algebra from your grade 10. You have these. So this is what we have here. There is something that is common here. let's see here, h squared, x squared, h squared. There's something there. X squared plus h squared. H squared plus h squared is equal to b squared. So meaning to say we can simply substitute this from what we got in triangle ADC. So c squared is equal to a squared minus 2ax. In place of this, we are going to substitute the equivalent to that, which is this part here. All right, let me just try and use this one. In place of this x squared plus h squared, there is an equivalent that we are given, which is in this case is the b squared. So we can substitute that with the b squared. Okay, look what we have. We are almost to the formula. Remember what we need this of this nature. This is written in terms of c squared. So it is given as c squared is equal to a squared. Take a closer look. A squared plus b squared. We have that condition here. A squared plus b squared. We have it here. A squared plus b squared. So c squared is equal to a squared plus b squared minus 2ax. This is what we have. Minus 2ax. This part is the one that is not on our formula here. Let me indicate it properly. Here, this x. On our formula, we are given this as a squared plus b squared minus, it is supposed to be, when it is like this, c squared is equal to a squared plus b squared minus 2ab, the cosine of c. Yes, we have this here. 2ab, the cosine of c. This is what you're supposed to have from this. This one. This is what you're supposed to have. But we have got x. So the question is, how are we going to eliminate this x? How are we going to remove this and have it in terms of b cos c? So think of that, b cos c. Just think of obtaining a cos from this triangle, but it must be cos of what, guys? Look, the cos of c. So do not waste your time thinking about the cos of b or the cos of a. We need the cos of a c. So let's find out. This is a right angle triangle. So we can find the cos of c from triangle ADC. All right, sorry for that. From this triangle ADC, all right, from triangle ADC, we can determine the cosine of c. That is the cos of c. Remember from the SOHCAHTOA concept, cos, adjacent over hypotenuse. So there, we are going to need adjacent over the hypotenuse according to the angle c. That is our adjacent. The hypotenuse is b. Remember, h there is the opposite. So the cosine of c being adjacent over the hypotenuse is going to be x over a b. So that is x over a b. So as we can see, we have got something in terms of the x that we want to remove. So let us have it as x as the subject, just over 1. Make x the subject, 1 times x. So x is equal to b times cos of c. So that is going to be b cos of c. We have what we need to remove from this part, which is x equal to b cos of c. And this is what we need to remove from this part, this x. So let us substitute this. So we are simply going to substitute the equivalent value that we are given. So therefore, c squared was going to be equal to a squared plus b squared minus 2a. In place of the x, we substitute what is equivalent to x, that is b cos of c. Guys, this is exactly the formula that we need, where c is the side to be calculated. This c is the side. Let me just write small letter c there. The side to be calculated. So the c squared is equal to a squared plus this. So that is what we can conclude. So by proving this, we have proved also that a squared is equal to b squared plus c squared minus 2ab minus 2bc, the cosine of a. We are also proving this at the same time. We're also proving that one written in terms of b. So are you able to prove this in exam? That is what they are testing you. So these are formulas. These are like follow-up. If you do not understand, just try to follow up. As you are following up, guys, you actually understand what is happening, especially the diagram, the expansion later on. You actually understand that. Just try to watch it again until you understand the concept that we are having there. So remember, this was for an acute angled triangle. What if we are working with an obtuse angled triangle? So in an obtuse angled triangle, they might give you a diagram having or showing an obtuse angled triangle. How are you going to prove the same concept of the cosine rule? So remember, we are going to have something of this nature for this to be obtuse angled at this point. So that is, we have got our triangle A, B, C like that. So you can even make constructions in this case to match that perpendicular height concept to point D. So this is not part of our diagram. It's the constructions thereafter. So this is side A, side C, and this is side B. Remember, the concept does not change, just like what we saw on the sine rule. If this is the obtuse angle, if this being the obtuse angle, that is our angle C, this other angle here is going to be an acute angle. This other angle is going to be an acute angle, and that is going to be 180 degrees minus C. If this is C, this is 180 degrees minus C. Remember the concept of angles on a straight line. And we do understand that for a cos, the cos of an obtuse angle, it's a negative of that of an acute angle. Remember the concept of a cos being negative. We shall talk about that. All right, so this is it. You're going to have something of this nature. Just understand your diagram. And also, let us consider, just like the previous case, we are going to take this time from C to D. We are going to let this to be equal to X. From C to D, we are going to let this to be equal to X. Meaning to say the wall of B to D is going to be A plus X. Remember, from B to C, it's A, and from C to D, it's X. So this A and this X combined together, that is A plus X from B to D. So there are a lot of things that we introduced here. So let us just write them. We let H to be the height. So that is what we had in this case from AD. So AD to be equal to H, which is the perpendicular height of triangle ABC. So that is the height of triangle ABC with the what? BC as the base. Take note, it is taken from the base of BC. So that is with BC as the base. Okay? With the BC as the base, or with base BC, guys, with BC as the base. So if we let this also, we had CD to be equal to X. So we're going to let CD to be equal to X. So therefore, we are obtaining the wall of the length of BD. So therefore, BD is A plus X. Okay, this is what we saw here, the wall of BD, A plus X. So therefore, BD is going to be equal to A plus X. So that's it. Let us work out our diagram to see those formulas. How are we going to generate them? We used the concept of the Pythagoras theorem in the previous case. That exactly is the one that we are also going to use. So from the Pythagoras theorem, theorem, we are going to notice this. In the first triangle, ABD, the bigger triangle that we are given there, that is, let us consider from triangle ABD. So that's the bigger, this one, bigger triangle there. Hypotenuse squared, which is C, is equal to the shorter side, which is A plus X. So we are going to have A plus X squared plus this other shorter side squared. This is what we have. From the same sense of the Pythagoras theorem, from this other triangle, which is from triangle, considering from triangle ACD, this one, from triangle ACD, the hypotenuse squared, which is B squared, is equal to the sum of the shorter side being squared also, which is the X and H. Remember, from C to D, that is X, so it's going to be X squared plus H squared. That is what we have. All right. Let us conclude just like the previous case. Expansion of the brackets here. So we saw that identity, it's a positive. So everything is going to carry a positive. That's going to be first term squared plus 2 times the first times the last plus the last squared plus H squared. So you can expand from that identity of A plus B squared, or just open 2 brackets there, expand them. It's one and the same thing. You are going to have this. Just like the previous case, we can see there is something common, X squared plus H squared, X squared plus H squared from the triangle ADC that we calculated. So this, since it is equal, let us substitute with what is equivalent to that. So this is going to be C squared is equal to A squared plus 2AX plus the part of X squared plus H squared. This part here is equivalent to what? To B squared. We're just substituting the equivalent of that. So the formula, if we are to check, we are almost close. C squared is equal to A squared plus B squared plus 2AX. This is where we are. We know that this is supposed to be A squared plus B squared, which is exactly what we have. And we are supposed to have minus 2AB, the cos of C. We're supposed to have something like that. So meaning to say, what is disturbing our formula in this case is the X that we are seeing here. So we are supposed to get rid of this X. From where? How are we going to get rid of this X so that we eliminate, we remove it, and substitute with an equivalent of that same X? All right. From this other part, we can see that what we need, like I said here, so that you can have a hint of what I'm trying to explain. Remember, we are going to have A squared plus B squared minus 2AB, the cosine of C. So there is a hint there. You are supposed to focus with a cos of C there. Not the cos of A, not the cos of B, but C. So we are focusing here with the angle C. Where the angle C is, remember this is 180 degrees minus C. Okay, let's write it. Let's write it. Remember, from our trigonometrical ratios, we can determine this. All right. So that is the cosine of 180 degrees minus C, the cosine of the angle in a right angled triangle. In a right angled triangle is equal to the adjacent over the hypotenuse. So that is the adjacent, which is X, over the hypotenuse, which is B. But let's get rid of this relationship of the cos of 180 minus C from the cast concept. 180 minus C, this is the second quadrant, which is the quadrant of sine. And cos here is referred to as a negative of the acute angle. So meaning to say, this cos of 180 degrees minus C is same as minus cos of C from reduction formula. That's minus cos C. In the second quadrant, where we have got 180 minus the reference angle, is the quadrant of a sine, not cos. Cos is a negative there. So it's minus cos C. It's different from the previous case where we had that of a sine. If it is sine 180 minus C, it is equal to the sine of C. Sine is just going to remain like that as a positive, but cos changes to a negative. Remember, your trigonometry also there plays a role. So remember, what we need is X. Here, we need X. So let us simply make X the subject of the formula from this. Cross multiply. That is 1 times X is equal to B times the cos, which is negative there. So that's negative B, the cos of C. So this is what we are going to substitute with in place of x into this formula that we are having here. So therefore, from this, we are going to have c squared equal to a squared plus b squared plus 2a. This is what you're going to have. 2ax, x. Your x is this one, minus b cos c. So multiply this 2a times this. It is going to give us minus 2ab. If you multiply these two, that's minus 2ab, the cos of what? The cos of c. So this is exactly what we are supposed to have from our cosine rule. So this simply means even that formula of a squared, whatever that you had before, is the same. By proving this, we have already proved that other part. So we are going to see, like I said before, when using these formulas of the c squared, the side squared, you are going to use that in the calculation of the sides. Then the other one, we are going to talk about that in the simplification where you're going to be calculating the angles. So that is it. There you are working with an obtuse angled triangle. That is what you're going to need when working with an acute angle triangle, because they are going to ask you with a diagram, if they draw a diagram for you, like the diagram is drawn already for you guys. It's a non-right angle triangle that you have given there. You must use this concept of a non-right angled. Is it an obtuse angled? You must use the concept of an obtuse. All right. Is it an acute angled triangle, or an obtuse angled triangle? Both giving us the same formula, which is this part. So you must end up with this formula, or whatever formula that you're given, depending with the proof that you're going to have, guys. It's in your hands, but you must have one of these formulas that is to prove that we are in the right direction. So we shall see more questions as we are answering our exam questions, so that we see how do they ask these questions and how are you going to attempt those typical questions. But for now, that's it till we meet again.